maybe we can consider the non-Riemannian geometry gravity. And one of the gravity framework that can easily avoid higher order derivatives is the Teleparallel gravity. So next, we try to consider the parity-violating model in Teleparallel gravity. First, I will briefly discuss what is the Teleparallel gravity. The equivalent principle tells us that the gravity can be regarded as a geometric effect. And in a general space-time, there can be geometry quantities such as curvature, torsion, and so on. The general relativity is the simplest gravity model in Riemannian geometries, which use only curvature to describe gravity. So, can we only use torsion rather than curvature to describe gravity? The answer is yes, and this is the Teleparallel gravity. It means the so-called Teleparallel gravity is to use the curvature, but not rather than use the torsion rather than curvature to describe gravity. And usually, we will use the metric and connection to describe the measurement structure and translation structure in space-time. But equivalently, we can also use chat and spin connection to describe the measurement structure and translation structure in space-time. The chat language and metric language are equivalent from the point of view of geometry. Although the chat language is more complicated, but it has its advantages. For example, in the Teleparallel gravity, if we use the chat language, then the Teleparallel constraint, curvature-free, and metric-compatible conditions can be equivalent that the spin connection is expressed by a Lorentz matrix. If we choose the chat and Lorentz matrix as the basic variables, then the torsion-free and metric-compatible condition can be automatically satisfied. There is a great advantages in Teleparallel gravity is that the torsion contains only first-order derivatives of the basic variable. It means that the Lagranges composed of torsion can avoid higher-order derivative automatically. So we don't need to care about the higher-order derivative problems in Teleparallel gravity. Okay. After clearing the geometry and the basic variable, let's introduce the Lagranges of the gravity. Can we really use the torsion to describe gravity? Here, we only have torsion. And the simplest scalars composed of torsion, there's only 3 independent scalars. To be fair, maybe we should consider all 3 scalars. But this Lagrange has 10 gauge symmetry, 4 diffeomorphisms, and 6 local Lorentz rotations. But when the coefficients satisfy this condition, the Lagrange has 6 more gauge symmetry. So this condition can make the Lagrange has the most symmetry. After this requirement, we can obtain the original Lagranges of the Teleparallel gravity. The overall factor can be absorbed into the gravitational constant. And here we normalize the gravitational constant G to be 1. So this is the Lagranges of original Teleparallel gravity, and it also called the TEGR model. We can surprisingly find that the TEGR model is equivalent to the general relativity because their Lagranges only different by a total derivatives. This is surprising result because even we don't know the general relativity at the beginning, we can construct a general gravity theory use only torsion, and it can be equivalent to the general relativity. Okay. Since the TEGR based on torsion is equivalent to the general relativity, and we have shown that the parity-violating model based on curvature always usually suffer from the gauge instability. So we think maybe we can try to consider the parity-violating model based on the torsion, modify the TEGR model. We want to figure out at least two questions. One, in teleparallel gravity, can we have a completely ghost-free parity-violating model? Second, if the answer is yes, what kinds of parity-violating effect could exist, and how these parity-violating effects different from the parity-violating model in Riemannian geometry? That we want to figure out. As a first step, we imitate the Chongqing's gravity. They introduced the topological and parity-O terms composed of curvature. So we introduced the topological and parity-O terms composed of torsion. And this term actually is the Lieyan term proposed by two Chinese, Liehua Tu.
I forgot the definition of the for
Oh, okay. Circle means the Riemannian geometry, and the tilde means the hot.
You mean what? This is just the star, the usual.
Yes, usual. Because
Why
here,
do you
because we use two kinds of curvature here. One is in the Riemannian geometry, just like the test ball of general relativity, and we use a circle on it. And the second kind of curvature is used to describe another connection in the space-time. It will be.
Is there a definition of even previous slide, or?
I have definition, but I can write it. I can explain. 要不我用中文解释一下。简单来说就是，其实我们这里。其实跟通常。
差不掉了，那。
没关系，我感觉我口头说的就是联络原则上它的度规是可以独立的，但是在这个黎曼几何里面呢，他们要求了这个无劳跟度规适配条件之后呢，联络完全由度规决定，这样得到的曲率呢，就是我这里带个零，上面带个零，就是说这是一个黎曼几何完全由度规决定的曲率。但是我还可以存在另外一个时空的联络，它跟度规是独立的。然后就通常的这个黎曼几何表达式呢，也可以用那个联络算出一个新的曲率出来，然后那个曲率呢，一般会跟这个黎曼几何里面的那个曲率是不等的。The non-Riemannian geometry. Yes, here we consider the metric compatible conditions.
Yes, and then you get a unique connections in the Riemannian geometry, right?
No, the Chongqing's gravity need the torsion-free condition, but I want the curvature-free condition. I will use the torsion is non-zero, but the curvature is zero. It means
so you mean curvature is zero everywhere, right? By curvature, do you mean this Riemann tensor or Ricci tensor or Ricci scalar?
Riemann tensor.
So every component of a Riemann tensor is zero.
in a small regions, yes, but we do not consider the
locally.
not 1 point, but because we can maybe there are some curvature effect come from the topology, but I don't consider the topology. I here don't consider the topology. We
connected region.
yes, connected.
Did this answer your questions?
Maybe afterwards. Okay, please continue.
Okay. So we try to imitate the Chongqing's gravity. They introduce a topological and Parity-violating composed of curvature.
In summary, so this circle, which means the metric is independent
of the circle means the usual textbook curvature. The curvature in the textbook.
In the usual sense.
Yes, in the usually textbook.
Okay.
And because this topological and Parity-violating is composed by the Liehuatong and Yanmuli, so we can call it the Lieyan. So the new model, I will call the new model the Lieyan modified teleparallel gravity, and I will call it the NYTG model for short. Okay. Next, I will discuss the NYTG model. I want to analyze its stability and its Parity-violating signals. Okay, and this is the Lagrange. And it modify the first term is the original Lagrange of
actually, if you look at this is exactly the same as G. So the point of attending parallel gravity is just add additional terms.
Yes.
But then you can also use it write it in Riemannian tensor.
No, 就是it can be equivalent to the Riemannian tensor, but this cannot be expressed by usual Riemannian tensor.
Really, but this T, I think this T has some equivalent expressions. No,
because only the original teleparallel gravity can equivalent to some gravity theory in Riemannian geometry. But when we modify the original teleparallel gravity, they will not equivalent to another gravity theory in Riemannian geometry. So this is an independent way to modify gravity. It means just like okay. Here is same, here is equivalent. But when they modify, they will not equivalent anymore.
Just one question. So this is equivalent even in the presence of matters?
If we consider the couple to fermion, it maybe will be some problems. If we only couple to the scalar field or the Yang-Mills field, it will be okay. If we couple to the fermion, the torsion effect will couple to the spin, and it may be some different effect that will violate the Einstein equivalent principles.
But how about couples to a say scalar field? Because in cosmology, scalar field is usually
non-minimal couple to the metric. We have metric here. We just couple it using the usual way.
Oh, so it's the same.
So the standard cosmology is not changed.
If we modify the Lagranges of the gravity, the cosmology will be changed because the Friedman equation will be changed. The matter is same, but the gravity part will be changed. The gravity part will be changed.
So the exact equation is still modified, but the energy momentum tensor remains the same, right?
Yes.
But is this true also as the perturb? Is this true only for the background level, or at the perturbation level it also holds? All this is irrelevant.
Here we have not considered the cosmology now. It is in general manifold, general space-time, and I will apply this model to the cosmology next.
If the Friedman equation is modified, is it consistent with current observation? Is it consistent with current observation of the universe? We have cosmology.
Yes, it can, because just like FR, it modifies the general relativity, but we can adjust some the
Parameters.
yes parameters.
There is some parameter.
That so the modification will appear in the very early universe or the very late universe, and in a period it will very similar to general relativity. So okay,
What about the speed of the gravity? So very similar with the Einstein.
it can be different.
It can be different.
Yes.
You can adjust parameters.
In this model, I will show that the left hand and right hand gravitational waves will have different speed.
Mm-hmm. Okay, like
And
so you can distinguish it by looking at this.
For the data of LIGO.
Okay.
But
if you can measure this polarization carefully, polarization, you have different speed for different polarization.
Yes, different polarization have different speed. Using some like Bayes analysis,
okay.
I don't know.
Suppose you, for example, you have a binary merger, and then it emits gravitational waves.
Yes.
And then it's detected by LIGO.
Yes.
And then you can measure this signal if you can distinguish different polarization on the detector. Yes. Okay. But right now, is there technology to distinguish this?
Because I'm not very clear because I'm not very familiar with the experiment, so I do not do the such analysis. But Wen Zhao in the
赵文
对， he did the analysis of our models, and he using the LIGO's data.
Okay. So I wonder, is this effect depend on frequency or
it will depend on frequencies.
So the best, I mean
the LIGO, the data do not show parity-violating effect for now.
No, yeah, but I mean, what about other frequencies like from theory? Can you tell a prediction on which frequency the difference is
obvious?
largest?
Yes, the lower frequency will more obvious. The lower frequency
will
be.
To observe it on CMB. Okay.
And the be obvious high frequency. So this is the model, and next we apply it to the cosmologies. And in the so-called cosmology, first let's look at the cosmology background. Usually, the so-called cosmological background is the background that the matrix and the matter is homogeneous and isotropic. If in Riemannian geometry, the connection is completely determined by the matrix, so the connection is also homogeneous and isotropic automatically. But this is not the case in teleparallel geometry. In teleparallel geometry, the connection cannot be completely determined by the matrix. So we need to additionally require the connection is also homogeneous and isotropic. And in this way, we can obtain the background of the teleparallel geometry, cosmological background of the teleparallel geometry. After study, we found that the parity-violating term has no effect on the background evolution. So if we want to know the effect of parity-violating term, we need to consider the perturbation. The background will be completely synced with the general relativity, but the perturbation will be different. So next we consider the perturbation. Because here the basic variable is Cheb and Lorentz matrix, so we do the cosmological perturbation on the Cheb and matrix. We do the scalar vector tensor decomposition because the scalar vector tensor type variables will be decoupled at the near perturbation level if the background is homogeneous and isotropic. Okay, for the scalar perturbation, we vary that there's one dynamical degrees of freedom, and it is indeed ghost-free. For vector perturbation, we found there's no dynamical degrees of freedom, so of course no ghost. And for tensor perturbation, we vary that no matter in flat universe or curved universe, the tensor perturbation is always ghost-free. For now, we have varied all the dynamical degrees of freedom in the NYTG model, and we show that they, of course, indeed ghost-free on all the energy scalar. They always ghost-free. So we successfully find a parity-violating model that is completely ghost-free. Next, we want to figure out what parity-violating signals are they. Let's consider the propagations of gravitational waves. And here is the propagation equations of left-hand and right-hand gravitational waves. We can find that the dispersion relation is parallel. It means the left-hand and right-hand gravitational waves will have different dispersion relations. If you make that the left-hand and right-hand gravitational waves, you have different propagation speed. And this phenomenon can be called the velocity birefringence phenomenon. For now, we have not observed such a parity-violating signals in the LIGO. So if you put constraint on the parameters of the model, of course, this phenomenon is in the late universe. Because the LIGO is from the two black holes versions, and if we consider the very early universe, for example, we consider a snowball inflation in the very early universe. We can find that the left-hand and right-hand gravitational waves will have different primordial power spectrums. Power spectrum is different. It depends on the snowball parameter and see the coupling of the parity-violating terms. Okay. Next, I want to maybe the time is run out. I will give a quick on the concept of irregular universe. What's the meaning of irregular universe? As I said previously, the cosmological principle asks that the matrix is homogeneous and isotropic. But in the teleparallel gravity, the connection cannot be completely determined by the matrix. Usually, almost all the paper assume that the connection should be homogeneous and isotropic too. This universe can be called the regular universe solution. And the regular universe solution was adopted by almost all the papers on teleparallel cosmology. But on the other hand, we can determine the connection by the gravitational field equations. The solutions will be not unique, and regular universe will be one of the solutions. The other solution, the connection is not homogeneous and isotropic. The cosmology background, which the metric is homogeneous and isotropic, but the connection is not. Such a cosmology, such a universe, we can call it an irregular universe. We want to know what physical effect could exist in an irregular universe. Of course, the different teleparallel, we also apply the irregular universe concept in the NYTG model. Next, we need to find the background, irregular fat universe background. We solve the gravitational field equations and the curvature-free and metric compatible conditions. We finally find this solution. We verify the symmetry. The symmetry of this solution. The metric is the usual FRW metric, so it is of course homogeneous and isotropic. But the derivatives of the connection along the Kuning vector field is not equal to 0. So the connection is not homogeneous and isotropic. Next, we consider the background evolution of the irregular universe. We surprisingly find that the regular universe and irregular universe have the same background evolution. It means that the symmetry of the connection will have no effect if we only consider the background. If we want to know how the symmetry of the connection affect the universe, we have to consider the perturbations. Okay, this is the perturbation. I only discussed the unique features of the irregular universe. When the connection is not homogeneous and isotropic, the scalar and tensor perturbation will be coupled at the near perturbation level. This is very different from our test bowl of the cosmological perturbation. Because our test bowl only consider the case the background is homogeneous and isotropic. But here, because the connection is not homogeneous and isotropic, the internal space of this geometry will be not isotropic. And it will provide a mechanism to couple the scalar and tensor field at the near order. It will cause there is a strong statistical correlation between the primordial scalar and tensor fluctuations. And maybe it will cause the correlation of T modes and B modes on CMB. Their correlation is not equal to 0. And it will can be tested whether our universe connection is homogeneous and isotropic.
So is this commonly happens at the sim scale? For example, this.
Yes.
Yes, it's at the sim scale.
But here we assume the connection is not homogeneous and isotropic. If the connection is completely homogeneous and isotropic, they will not couple at the near order.
But in the standard inflationary symmetry, usually the universe is homogeneous and isotropic after the cosmic expansion. So that being said, this candle effect is only effective if it exists as the very first few falling of inflation.
Yeah.
But can we detect such physics because we might need something the complete variance, which makes this effect not distinguishable.
What? 什么？
So the effect should happen at the very first few inflation.
First
inflation.
Yeah, inflation.
Very early of the inflation.
Not only in the very early inflation can be happening because here the metric and the matter is homogeneous and isotropic, but the connection is not. It will not happen in Riemannian geometry. It will happen in Teleparallel geometry. Their geometry is different. It means if we consider the general relativity, Fr, whole density, the host, they are all in Riemannian geometry. So if the metric is homogeneous and isotropic, the connection must be homogeneous and isotropic. But if in a geometry that the curvature is zero, but torsion is non-zero, that can happen that the metric is homogeneous and isotropic, but the connection is not homogeneous and isotropic. It is possible that that can happen. But this concept of irregular universe is almost no one studied it because maybe it is some effect is not will be disfavored by the experiment.
Non-homogeneous and isotropic connection.
Yes, the connection
means that we have a homogeneous and isotropic background.
The metric is yes.
Metric, yes.
The matter if the scale only do not consider the fermion. The matter can be also homogeneous and isotropic too, but the connection is not. Do not consider the fermion. It will not happen in Riemannian geometry. It only happen in other geometry.
This homogeneity can survive even after inflation. This is what we are.
Yes, even after the inflation, the metric and the matter and the usual matter is homogeneous and isotropic. But the connection maybe is still not
What is the typical time evolution of homogeneity connection? In GR, if you introduce inhomogeneity or anisotropy of the metric, then this guy can decay. And if you turn on this type of inhomogeneity in connection, how does it work?
For example, in a typical universe, the anisotropy scales as the energy density of anisotropy scales as A2 minus 6. So it quickly decays in an inflationary universe. So I think Toshi is asking, how is this homogeneous and anisotropic connection scaling? How it evolves according to this scale factor or cosmic time?
This was your question.
用中文说一下。
就他们动力学演化是什么？
Oh, good question. The answer will be the small f is the small f and bf can be arbitrary smooth function. So it has no dynamical equations on the background. It will disappear on the background. It will disappear on the background. We cannot obtain a background evolution about the small f and bf because no matter small f and bf are any smooth function, they can satisfy the gravitational field equations and the geometry constraint. So the small f and bf just disappear in here. It just disappear.
Does it mean that this is not a dynamic degree of freedom?
Yeah. If you only consider the background, yes, we cannot get any dynamical equations. It is very strange, so almost no people to study it.
Is it degrees of freedom?
Case
Gauge.
是什么？
gauge.
Gauge. Then not completely the gauge because here the gauge symmetry is the gauge symmetry kill the small f, but cannot kill the big F. I tried it.
So this means small f is a first class constraint, and f is a second class constraint. So do you know the terminology of Hamiltonian analysis?
Yes. But the Hamiltonian analysis, they do not need a background because they can apply to any background, not just cosmological background.
Okay. So if F has some space coordinate dependence, then it appears. Only when F is homogeneous, it disappears.
It only disappears on the background. If we consider the perturbation, it will have effect.
Okay. By background, you mean homogeneous.
The geometry is yes.
Okay. Nice.
Oh, it's better to be quick because the 8 minutes.
Okay. Okay, I will get quick. Oh, we want to consider.
We have only 2 talks, so probably we will be flexible.
I think there are 3.
There are 3 talks today?
Yeah. And the last one is about my.
Oh, the schedule has changed. I see. Okay.
Sorry. Yeah, I think we can discuss during dinner or after the third talk.
I will finish it in 5 minutes. Okay.
Sorry.
Let's consider the extension of the NYTG model because I want to know whether the NYTG model is the only one ghost-free party-violating model. We consider the extension. First, we consider we abandon the topological properties. We consider all the party-violating terms, which is quadratic in the torsion tensor. But they are not independent. Only P1, P2 are nearly dependent. P3, P4 will be expressed by the nearly coordination. I can prove it because using some geometric identity, Bianchi identity. I'm not showing it here. And after our study, we find that if you suffer from the ghost instability again, unless it completely reduced to the NYTG model. So even though the NYTG model is ghost-free, if we extend it into the most general party-violating term, which is quadratic in torsion tensor, it will suffer from the ghost instability again, unless it completely reduced to the NYTG model. Okay, it seems the NYTG model is the only one completely ghost-free party-violating model. But maybe it's yes. I want to know whether the answer is yes. So I have to try to more general party-violating model. So next, I consider extend it to a scalar tensor model. So next, we consider party-violating scalar tensor model in teleparallel gravity. Next, we have to find all the party O terms. We only consider the party O terms that satisfy the following three conditions. First, we only consider the nearly quadratic torsion term. Second, we allow the torsion to be coupled non-minimally coupled to a scalar field. 3, we forbid the high-order derivatives. Naively, we can write down maybe more than 20 party O terms, but they are not independent. In order to find out the independent party O terms, we use the technique of decomposition of torsion. We decompose torsion into 3 kinds of torsion according to the irregular representation of Lorentz groups. And using this technique, we finally find there's only 7 independent party O terms can be insist. So we use this party O terms can find out a very general party-violating model, scalar tensor models. And we want to figure out whether there's other ghost-free party-violating model in here. To make the discussion more simpler, we consider a more simple model, which the party-violating term is composed of 7 independent party O terms, multiply the 7 independent functions about the scalar fields. And after our study, we show that generally the model will have ghost modes and strong coupling issues. but there are some conditions can kill the ghost modes and kill the strong coupling issues. Condition A and condition B will be okay. Both condition A and condition B are okay. After our studying the gravitational waves, the parity-violating effect is very familiar. It's very similar, similarly with the NYTG model. It will have velocity birefringence in late universe, and it will cause the primordial gravitational waves are different. But the condition B I mentioned above, will kill the parity-violating effect, and this is what I don't want it, because I want a parity-violating gravity. I cannot kill the parity-violating effect just because maybe it goes free. So finally, we should only consider the condition A, which can make the model ghost free and keep the parity-violating signals in gravitational waves. That's finally is the summary. First, I briefly discussed the parity-violating gravity in Riemannian geometry, and usually it will have goals. Then, because the TEGR based on torsion is equivalent to the GR, it provides us with another way to modify the GR. So we try to modify the TEGR to obtain a parity-violating gravity. First, we try the NYTG model, the simplest model, and it is indeed a ghost-free. Then we consider it is extension. Finally, we find some ghost-free, potentially healthy parity-violating scalar tensor gravity. They are ghost-free, have the velocity birefringence phenomenon in late universe. If consider snowball inflation, the power spectrums of primordial gravitational waves are chiral, the left hand and not equal to right hand. And it is because it will be more obvious at low frequency, so it is an infrared effect. Okay, that's all. Thank you. Any question? 晚饭再说。Okay. We can discuss in later.
给了吗？
你下了没有？
你的 WeChat 是关了吗？哦，
是要再重新登吗
？WeChat 是在哪？WeChat
插 U 盘。
这就是 U 盘插不上，我才能那个正好。
那你重新把WeChat。
WeChat 哪个是 WeChat？
你重新搜索。
哦。
你可以点一下那个 WeChat 打开，晚点我给你。行，然后你在真的，是这里。收到了是吗
？Yes。
下来好了，下来了。然后在那边左上角，右下角。
也对。
那你把这个退出来，因为它会吵的。
好。
右键，不是，ignore， 然后右键退出来。好了，然后你把那个弄一下，对不对？对，可以开始吗？
好，可以。So we start right now. Okay. Where is this? So, shall we start now?
Yes.
Okay. So hello everyone. Today I'm going to talk about some recent not recent work. I think in this January's work with my collaborator, Professor Yongcai, who is in Zhengzhou University, about the study of parity-violating in terms of bouncing cosmology, which will be mainly based on these publications. And if possible, we can also talk about some ongoing projects. Okay. So let's talk about some parity symmetry. So probably all of you knows that, right? A parity symmetry means that the symmetry under a point of reflection, and we know that in the real world we can have a parity asymmetry which can be traced back to the year of 60s. The work from Yang Chenning and Chen Dao Li about the parity asymmetry in the weak sector, but in the terms of cosmology, it is usually assumed that the cosmology is parity symmetry because in the study of cosmology, we are based on the general relativity, which is totally parity symmetry. So that being said, if you make a point of reflection of our universe, there's nothing to change. However, I think in the recent 1 or 2 years, there is a growing interest on the possible hint for the parity violation in the large scale structure and in cosmology. Here, I think I have listed 3 of these papers, and the first one is about the cosmic microwave background, and then we also dedicated the parity asymmetry in the galaxies, which is in the large-scale structures. And I think the third one is also about these large-scale structures. And in view of that, we observe such a parity asymmetry. And or maybe let me be more precise, we have some hint for this parity asymmetry in the large-scale structure and the cosmology. So now it becomes possible for us to search for new physics through these parity asymmetric signals. And so we have some basic logic about how to describe this parity violation effect. So firstly, to describe this large scale structure, the one of the most foundation of our cosmology is where you are sharing chat. Okay, hello. Okay. So shall we continue? Okay, so in cosmological perturbation theory, you know that our universe starts in extremely high energy scales with extremely small size, and in which we have the quantum fluctuations. And as the universe evolves, these quantum fluctuations enters the horizon and becomes classical perturbations, which then evolves into the current large-scale structure. So as we observe this parity asymmetry in the large scales, it is natural for us to come to cosmological perturbation theory to see if this parity asymmetry is hidden in these perturbations. And this perturbations is originated from quantum fluctuations. So we have to talk about these statistic properties that inside these correlation functions. And we also know that in the standard perturbation theory, you can classify these perturbations into these scalar, vector, and tensor modes, right? And moreover, at the linear level, these 3 kind of perturbations decouples to each others. And finally, we know that in the standard cosmology, the universe starts with an inflationary epoch in which the universe expands around e to 60 times. And we know that the vector perturbations it scales as a2 minus 2. That being said, in the epoch of cosmic expansions, every possible vector modes are perfectly diluted out. And on the other hand, both the scalar and the tensor modes becomes frozen after they become super horizon. That being said, in today, the vector mode is actually suppressed, and the scalar and the tensor fluctuations generated in the primordial universe remain, and we can observe these modes. So now we are clear that to find out this parity violation effect, we need to study the correlation functions of these scalar and tensor fluctuations, right? And then, okay, and then when we know that the leading non-trivial parity violation observables is the scalar trispectrum and also the tensor power spectrum. So is this clear? So because in the tensor sector, we know that you need to in the standard GR we have two polarization modes, the conventional plus and cross mode, which itself carries a polarization tensor.
Yeah, I'm sorry. I think previously you talked about the vector, but I forgot.
Oh, okay. Vectors. Do you know how to screen back this PPT? This one?
Yeah.
Oh, but I didn't. So the issue is that sorry. Is there anything to write?
I can use the blackboard.
Oh, it's very easy. These two tensor degree of freedom, and we also have this time translation symmetry, right? So there's no complete evolution, but in the real study, we will also have a scalar field. We'll always add a scalar field, right? In simply setup. Then now you have two tensor degree of freedom. You have one. Let's say we only through one scalar field, and you do not have this vector degree of freedom, right? So if you use this minimal setting, then you do not have this vector degree of freedom. Notice that this degree of freedom counting is not to be conducted in a perturbation theory. So this is valid for any manifold, or of course we'll always consider
So that's no degree of freedom.
So firstly, you do not have this guy, and even if you add this guy, and for example, some people say that.
What about matter field?
Yeah, you can either, let's say you can say that, okay, I always have something like Maxwell, and then what happens? And if you add something simply as simple as Maxwell, then you write down the momentum constraint, or let's say that this Einstein equation is 0I component. Let's denote this vector degree of freedom, this Fi, right? And after some mathematics, you will get it. So it equals something. So let's say that of course there is some ambiguity about this formula. So if you do not have anything like Maxwell, you will always get this Poisson-like equation, right? In the is Einstein G0I equals T0I equation. But this just means that if you do not have vector degree of freedom, this is not a dynamic equation because it does not contain timing derivatives. You only have this Poisson equation. But the issue is that you have this guy, this scale factor 2.
You mean the dilution?
Yes, so you always get a solution like F is A2 minus 2 with something. This is dependent on the scalar field.
But that if you use this as Maxwell input like that, but it will like add for example like phi FF kind of.
Oh yeah, well, actually we are doing something like that. we are doing something like that with Professor Chen Shan Ling, but unfortunately, it is very, very difficult to overcome this A2-2 suppression.
I think there are some ways.
Yes, there are. I think that, for example, he has a paper about a broken U1. More than in the context of inflation.
Yes.
So
yes.
Yeah. So, but usually this means that you need a very specific ways to turn on this vector degree of freedom. And if you have inflation, you also need a very, very specific choice to make it sizable to account for these observations.
So you can have a parity-violating vector.
Yes. So if you can, but I think if you can have this kind of ways, I think for these people, they are more interested in how to generate a primordial magnetic field, right? Because
I think
of course,
you can borrow this model from.
Yes, so basically you can always do that, but this vector suppression of vector mode is a generic common, because usually people in this field do not like to consider this. I think they just think this to be an extreme case. So surely you can manipulate your theory. You add some vector field, you made some kind of fine tuning, you may have some non-trivial coupling in this vector and maybe scalar, maybe tensor sector, and you have a sizable vector mode. But usually you have to do it with a lot of cost.
Yes.
So this is when we stating in a generic sense, people usually automatically exclude this. But of course, it is something doable.
Yes.
So,
yeah.
So
Okay.
Is this clear?
Continue.
Okay. And then we are saying that usually we will have this scalar and tensor degree of freedom, which is generally sizable after the cosmic expansions. And then we are saying that we need to study its correlation functions. And then we know that in tensor sector, there is no problem because tensor itself has two polarization modes. Each of them will characterize it with the polarization tensors. You can just add any parity violation effect by in this polarization tensors, this polarization vectors, there's no problem. But for the scalar sector, the problem is that you can only have a non-trivial parity violation effect starting from this scalar trispectrum level. That is the 4-point correlation function of these scalar modes. So we can have a quick look at why there is no signals from this scalar power spectrum and bispectrum level. Naively, you can think it in this way. So if you have this, the left hand side is this 3-point correlation function, right hand side is a 2-point correlation. You can always place this 3-point or 2-point in the same plane, right? And you make a reflection. But there is no difference, right? You have this guy, you flip this guy. This guy is identical to this guy. So also this is also true for the bispectrum case. You have this triangle, you flip it, and then you get a new triangle. But this new triangle is just identical to the original one, right? But you see that in this kind of, in the case of trispectrum or this 4-point correlation functions, you cannot place all these 4 points in a same plane, and then you make a friction. And you can immediately see that the left hand side is different from this right hand side. So,
so here you are saying that in order to see parity violation in 3D.
Yeah, in order to see the parity violation effect in the correlation functions, So we need to, for scalar sector, we need to come to this scalar trispectrum. Actually, I think this is one of the main focus of the community, because a lot of work has done. Because in previously there is a no-go theorem actually stating that. Yes, exactly. That no-go theorem is proposed by him and later revisited by I think in this year's June, maybe. And they also provided some years-ago examples. Say, for example, in the ghost inflation, which broke some of these conditions of the no-go theorem, and we are still thinking about that. So that being said, it is also not easy to generate something in the trispectrum level, and also the calculation for this scalar trispectrum is usually much involved. So, but in principle, we can have it in this trispectrum level. So, but we cannot have this parity-violating effect in this bispectrum and this power spectrum level. Is clear? Okay, so shall we continue? Okay, so or maybe someone would prefer to. Yeah. Yeah. Okay, let's say that for example, let's come to this power spectrum level. Let's say that we have 2 points.
You can just say that in order to have a left-handed system and right-handed system in 3D, super function have just a simple line in 1D, and super function design linear something in 3D. That's why you.
Because if you have something like 2D,
you can equivalent to rotation.
Yeah, yes.
So for example, you have this. It is a 2D.
So
you flip it, but this is nothing changed because you just do a simple rotation.
Okay, so
it recovers.
In this case, it's equivalent to rotation, but if you consider 3D, it cannot be done by just a rotation.
It cannot be recovered by any rotation and translation.
Okay.
So,
okay.
Also, maybe someone would more prefer some formal statement, right? So if you want to do some more formal explanation, then you can think about that. If you have let's say that we have a Jia is parity preserving, and if you want some parity of violation operators, right? You need some kind of parity violation operators. Let's write another simplest. Let's say for example this epsilon ijk. And then you have this scalar power spectrum. When we can write down its possible parity violating operators in the sense of EFT. Let's say, for example, let's randomly write down this guy. Let's randomly write this, but this is nothing but a total derivative. So nothing happens. So you have to come to this trispectrum level. You can have something like, for example, this phi partial I, phi partial j, partial k, phi, something like that. Because you have this epsilon ijk, you need 3 partials to have a covariant action. And use point intervals. This is just a total derivative, possibly after integration by part. So we have 2 kind of explanations about this. Why we need to come to the trispectrum level in the scalar sector.
Okay, I hope this this is clear and we can continue. So we are doing something actually very simple. So we are thinking about where could this parity violation if it happens in this universe. And we know since you know that everybody knows these figures, right? And you know that in the previous literatures we have this one stating that there's a new physics. We observe this polarized light in the cosmic microwave background. So naively, we might say, okay, how about we come to the scenarios before the formation of this CMB to search for this parity violation signals, right? And usually this means that we need to come to this primordial universe. Namely, conventionally, it is the inflationary scenario, right? In which the universe expands about 60 E40, probably 62, but and then we can have after a short reheating process, and we can have this standard thermal history of our universe. So it is natural for us to consider the scenarios before the CMB, inflation, maybe reheating, but and maybe some radiation dominations. But usually, I think people would tend to come to the study of inflation, and as there are many unemployed physics, and which also inflation has a very high energy scales. That being said, if you come say from the level of EFT, there can be more EFT operators in this stage, and there are more possibilities to explore in this scenario. So, but I think yesterday Dr. Shitong has given a talk also about his work, right? In his this is his paper in the year 2019, collaborating with Hao and Yi. So, which stating that you have no parity violations signals from the correlation functions at the tree level in the inflation, or more precisely, it should be exact theta space time, right? And with assuming only 3 conditions, that is, the universe has a scale invariance. And notice that the scale invariance is not in the common meaning that you have a scale invariant power spectrum. Well, okay, maybe you know, but I need to mention that because everybody makes mistakes about it. Everybody will hear about this. They say that, okay, by scale invariance, do you mean scale invariance power spectrums? And but actually, it is something that you make anyway. Let's do it like this way. So by scale invariance, it means that you do this. You change your universe scaling, but the physics remains invariant. But however, if you want to do this matrix, right? If you have a FRW matrix, let's write, for example, in terms of the conformal time, and then you immediately find that this scale invariance is almost equivalent to exact the theta or anti-the theta space time. I don't know if there is any exceptions, but it's just a simple deduction. You substitute this guy into this guy, and you require these two identical. So you immediately get exact the theta or anti-the theta spacetime, and this is just the standard inflation with a slow roll parameter is 0. So basically, this first condition and this from inflation is a little bit coincide, and then the second condition you means that we only have there's no, so we need to charge this laptop. Where is isn't here? No. Is this a real charger? This side. Like this. It has a very low battery energy. So let me see. Yeah. Oh, it's not successful. So I think this is almost auto.
Yeah, I think it's okay.
It's okay.
This is a slow charger.
Okay, so let's see.
Let's continue.
Already charged.
Yeah, no, it doesn't
charges?
matter. Yeah, doesn't matter.
Oh, it's in charge. So let's
Very slow.
continue from this point. Oh. But as long as it's charging, it's okay, right? And also, obviously, if you add another degree of freedoms, for example, you add a vector degree of freedom, because vector itself also carries a polarization tensor. You need to decompose this vector degree of freedom into this basis, and you can also get some parity violation. So the second assumption just says that you have a scalar field, but this is a very common in the study of cosmology, as most of our study just assume additional scalar degree of freedom in addition to the gravity, and then we will need to also assume this Bunch-Davis vacuum, which just means that when you choose the initial conditions for this perturbations, because it has a quantum origin, so you assume that this perturbation overall is in its lowest energy state, which is also seems very natural assumptions. And you see that if we have these three assumptions, but actually it works in almost most of these inflationary scenarios, then you have no parity-violating signals, and you need to go beyond. And actually, in these years, many studies has been proposed to go out circumstances no-go theorem. For example, I believe in this April, there is a paper studies how a non-Bunch-Davis vacuum can help to enhance this, generate these parity-violating signals. And also in this June, as I said, those guys revisit this no-go theorem and also give some example in a ghost inflation. And in that case, you have a ghost condensated scalar field, so that in its vacuum state, it is not scale invariance anymore. So this first condition is circumstance, and then they get some non-trivial results. Okay, so this is the first problem when we consider the parity violation from this inflationary scenario. And another problem is that if you have a standard slow roll inflation scenario, right? You know that we have the inflation can be characterized by these slow roll parameters, and usually this slow roll parameters is relatively small, right? And then if you, let's say, for example, in the viewpoint of effective field theory, then let's say that you write down this effective field theory UFT operators for these parity-violating signals, and we find that all these coefficients, all these coupling strengths, is all proportional to these slow root parameters, right? And that being said, even if you can have some non-trivial parity violation, but their strength is proportional to all of these slow root parameters, and as a result, because your slow root parameter is small, right, then your final result is suppressed by this slow root parameters, right? So these are the two problems when people come to this.
For example, I don't know why it's related to parity.
If you have this, I think in the revised paper they did some argument from the symmetrical and no. I forget about that in his study if they directly use the form of the mode function, but in the new paper, this guy just start from a symmetric argument, and then. But I forget about the details. But I believe in some of the deductions they use this scale inverse invariance properties to do some simplifications for these correlation functions. If you want to, yeah. Well, I think this is because you need to have some. I forget. I think in my laptop I have that paper, but up to now I cannot. The issue is that we are adding something in the scalar sector, right? Basically, their study is that okay, I have a standard gravity. Which works.
You use the wrong thing.
I forget about that. But in principle, this it should work. But no problem. So let's turn back to this slide. So we need some parity. So you need to add these operators like for example ijk. This kind of operators makes difference when you compare to different parity. And then, but you need a covariant actions, right? You need a covariant actions. For example, in this 2-point case, you need this partial I, partial j, partial k to contract this ijk operator, right? And if you have this kind of you see that after making a Fourier transformation, this is nothing but ki. This is kj and kk. So if you write it down, I believe the only allowed operator is something like phi partial I phi partial minus partial square partial j phi partial minus 2 partial k phi is something like that. But anyway,
I think you can use this.
Okay, but maybe we can come to that new paper if we have right.
Oh.
Yeah, maybe we can talk about it later, right?
Yeah, you can.
Because I can use maybe I can directly send you that paper, but we can have a. No. I think we need to close this. Oh. But the issue is that if you write down this kind of parity violation operators, it contains this kind of phi, and you do this. I believe in some of steps they use the substitute this scale invariance in this, or maybe we can study the technical details if you are interested, right? because that's a paper surely worth more investigations. So, okay, maybe we can continue at first, right? And then maybe I can send you that paper. So now we have say these two issues. One is the no-go theorem, which means that you need to go beyond the conventional construction of inflation models, and also you need to think about some way to avoid that this parity-violating signals is suppressed by the slower parameters. So actually, our work is very simple. In alternative, we consider that what if we consider the parity-violating in some scenarios different from inflation? Actually, this is a very conventional movement in the community because inflation is actually very well. It both from the conceptually and observationally. There is only some minor issues of the inflation theory. For example, this naturalness problem and also this singularity problem. And in the cosmology, in the past 10 or 20 years, people once are very interested in the so-called initial singularity problem, which actually pointed out that if your universe is always expanding, or more specifically speaking, their theorem is that if the average expansion rate, which is denoted by the average of the Hubble parameter, that being said, you integrate the Hubble parameter over time and do this average. If this kind of average expansion rate is positive, then when you trace back to the past infinity, you will always meet an initial singularity, which means that any geodesics in this universe is not geodesic incomplete. This is founded in the year of 2001 and 2003, two papers. And then in that time, people are very interested in this singularity problem. And people said that, okay, let's think about that. Let's just simply add something which is not expanding in parallel to the inflation. That is, say, for example, we can have something contracting universe, and somewhat this universe transit into an expansion stage. And but surprisingly, you know that the Penrose-Hawking theorem stated that you will always have a space-time singularity in the universe when the average weak energy condition is satisfied. So, but when people started to think about this cosmology to avoid the initial singularity in an inflationary universe, for example, you add a contracting phase, people find that you need to actually violate the null energy condition, or more precisely the average null energy condition, in order to avoid these singularity problems. But later on, people found that this kind of violations is actually very, very difficult to achieve. For example, in the context of gravity and also an additional scalar degree of freedom, and people found that you have to come to a extremely complicated, involved. Actually, in my PhD study, I did one of this. I believe our model is first covariant models to solve this problem in to have a healthy non-singular cosmology, solving this initial singularity problem without any pathology. But the case that is you have to involve a very, very complicated theory. And then people find that if you need such a case to avoid this initial singularity problem and you come to this so-called non-singular cosmology, it might be problematic. So in these years, people are not very interested in this context. But in our study, we are thinking about that because in this kind of, as we said, that this scale invariance is actually a very, very strong condition. Basically, it's just constrain your background geometry to be inflation, right? Because you cannot have an exponentially contracting universe. So the only solution is only realistic solution for a scale inverse universe actually this cosmic inflation. So if you come to this non-singular cosmology, it seems that the no-go theorem is broken in the pre-inflationary scenario, right? And also, similarly, because this slower parameter is characterized by the deviation of standard inflation, right? And now you do not have this inflationary scenario at all. Then you will always get a slow rope, unsuppressed slow rope parameter. For example, in a typical scenario, the so-called matter bounce scenario, in which we have a contracting phase in parallel to the before the expansion stage, where the contracting phase is dominated by a pressureless matter. In there, the first slow rope parameter epsilon is 3/2, which is actually of order 1 instead of, in the case of inflation, which I believe is at least order 10 to minus 2, 10 to minus 3, right? So we are thinking about if we can find some parity-violating signals, given that in this non-singular cosmology, given that it can simultaneously solve the initial singularity problem for inflation, and at the same time, the parity-violating signals seems naturally arise from this kind of scenarios, as long as you have a parity violation action. Okay. So basically, this is our motivation, and so actually we are basing on this study, but you know that if the study of non-singular cosmology is reliable or not is also still in depth. So we must be careful at the very beginning. But the issue is that surprisingly we find that we know that in this kind of non-singular cosmology we need something non-expanding to break the condition for the initial singularity. Let's say we have some contraction phase, but then we need some transition phase, right? Such that the universe suddenly transit from a contraction phase to an expansion phase. This phase usually we call this a bouncing phase. And in the study, people found that this contraction phase is relatively simple and healthy. And but this bouncing phase is problematic. You need to violate the non-linear condition and add a lot of actions, strange actions, to cure the accompanying pathologies in this phase. But in other sense, the bouncing phase is also, if exists, also contains some new physics, right? Because in the contraction phase, you can, it is composed of a normal scalar field with simple constant equational set parameters. This is not new, but in this bouncing phase, on the other hand, you need to add a lot of string series of EFT operators. That being said, the new physics actually probably lies in this phase if this whole scenario is true. Right? Or maybe we can naively see from the energy density. We know that if we have the gravity minimally coupled to these matter sectors, the background energy density is evaluated by the first Friedmann equation, rho equals 3h squared. And in the contraction phase, the hyperparameter is decreasing, right? Because it is contracting. So this A just decreases, and as a result, this is minus, and then your energy density just increases. And then up to its maximum, then some new physics happens in this bouncing phase. So we do not know how to evaluate this physical energy density at this phase. Or more precisely, it is very difficult to evaluate the energy density in a simple manner, but it's always doable. And then you have finally this expansion phase. Usually we take it to the, we can either take it to some inflation or simply the radiation domination, to just simply start the thermal history of our universe. In either case, the energy density, you see, for it is, especially if you take this to this radiation domination phase, this energy density is shrinking, right? That being said, this bouncing phase has the highest energy scales in this whole evolution of our universe. So naturally, we expect that if there is new physics, it should be more important in this phase, right? So, so you know that bouncing cosmology has a lot of problems. So actually, this study is just a very preliminary check on this topic. I believe there is a lot of following up works to do if we really want to study in a concrete manner. So our paper is very simple. We just find a result that we can have a sizable parity violation signals in the tensor power spectrum, but it is produced in the bouncing phase instead of this contraction phase. This is a little bit to our surprise because, as we said, that it seems that this contraction phase already breaks the conditions for this no-go theorem for inflation, right? At least it breaks the scaling variance. It also has an unsuppressed slow-roll parameters, right? So at first glance, including some previous studies filters, okay, I can generate something in this phase, some parity-violation in this phase. But in our examination, we said, no, it's the parity-violation phase is in this phase. But this is not bad because, as we said, the bouncing phase has the highest energy scales, right? So we use that as a new physics is actually less in this region. So the result is twofold. That means that if there's new physics, we can generate some parity-violation in this bouncing phase. And on the other hand, if we can confirm both this non-singular cosmology and also the existence for the parity-violation signals, maybe we can trace back to get some new information about the new physics in this bouncing phase. So this is the main result. And then we have this technical details, but I guess we do not have many times, right? We only have 9 minutes. Yeah, we have 9 minutes. So, but basically this technique is very simple. So basically you add these actions in which you have this scalar field, which is labeled by this LH. LH is actually the Hondesky action. I write this for the complexes because Hondesky theory is first it is regarded as the most general scalar tensor theory, like I said, the theory with 2 tensor degree freedom and 1 additional scalar degree freedom, right? And then add parity violation operators. In our case, we just take it to be the simplest Chern-Simons term for simplicity. And this term is used to cure all the pathologies in the bouncing phase. In here I just label it to be something HE to stand for that. This is something emerged only in the bouncing phase in this high energy scale, right? And then you can write down. But one nice thing about is that both this parity-violating action Ag and this action LHE, this term used to cure the instability of bouncing phase, is is irrelevant to the background evolution. So you can simply write down the complete way to parameterize in the previous studies, in which the starting from a contraction and a short bouncing, and here we, for simplicity, take the expansion phase to be a radiation domination to match the standard thermal history of cosmology. And then you have this background, and you can write down this tensor perturbations at quadratic level, in which the parity-violating signals is included in this, and this part is just the standard one, right? And then, since this Chern-Simons action is only relevant for this IJK parity-violation part, then you can simply get this mode function for these tensor fluctuations, and then you can simply get this gamma k in its standard form. And for our purpose, we choose input this parameter Pij to, and also this lambda to denote the chiral of this the tensor fluctuation, such that this lambda r is 1 and lambda is L, and we also input a neutral one equal to 0 for clarifications. And for our purpose, we are interested in the difference of each sector. That means that the difference for the tensor power spectrum is the left hand side and right hand side, and we normalize it with this summation. Right? So that's delta chi means the ratio of the parity-violated part over this whole tensor power spectrum, right? And then everything is just standard straightforward. You have this tensor fluctuations, you evolve it. This is just a very simple mathematics. Just solve this dynamic equation and solve this tensor power spectrum, and that's it. And why we are interested in delta chi, for example, I take an exemplified figure from this paper, and in which you see that this, because in the ongoing ground-based project like LISA and Tianqing, we can actually detect gravitational wave in this range, right? So to detect this kind of signals, first we need a strong enough signals, gravitational signals, right? This can origin from something like induced gravitational wave, or the bubble collision, or first order transition, first order phase transition, or something else. And then on top of that, we can have some parity-violation operators. For example, this blue and the orange one, and we can so you see that the problem is twofold. We need need an enhanced gravitational wave signals, and then on top of that, we need an additional parity-violated physics. So for our study, we do not explain where these enhanced gravitational wave signals come from. We only explain if this gravitational wave signals is enhanced, such that the future detectors can detect it. Then how can we distinguish them by this parity-violating signal? Okay. So that's why we mainly focus on this parameter delta chi. And after some evolutions, which is both standard way to calculate this tensor power spectrum, and you can simply find that this here t smaller than 0 is the contraction phase. This is the bouncing phase. This is the expansion phase. And you can simply say that, okay, this parity-violating signal is coming from here, this bouncing phase. So Okay, I also have some semi-analytical investigation explanations, but I guess this is not very relevant. So let's talk about future directions. So firstly, as we explained, we need to say, can we have a large detectable suppress the primordial gravitational wave signals, because we know that at the same bill range, the tensor fraction is much smaller than a scalar one, right? So on the first step is that you need a large gravitational wave signal for you to be detected in the future experiment. And also, we can also consider scalar by trispectrum, but usually this is very difficult because the mode function in the, even if we consider only the contracting phase, the mode function is much more complicated than in the inflationary case. So we are having some ongoing project on the tensor bispectrum, but the complexity is already very involved in calculations. And then the third problem is that given that if we rarely observe these parity-violating signals, given that this is actually from this non-single cosmology, how do we trace back this exotic physics in the bouncing phase? How do we trace back the high energy physics in this bouncing phase? And also finally, as Dr. Rao reported, the Chern-Simons gravity is not ghost-free. And actually in our study, we found that the delta G grows linearly on very small regions. But this is just because you choose the Chern-Simons theory, right? Then in this small scales, logically you meet this ghost. So you must cut it off. So this is also some in relation to his talk, that if we want healthily to provide the parity violation in all scales, we need some ghost-free theories. And okay, so that's for this talk, and thank you very much. So do you have any questions?
If you consider Chern-Simons coupling, you are in prediction of parity violation.
I think in their theorem, no, I think in Yuehang's recent result, no, because they say that you cannot have it. Oh, sorry, but they say that it cannot have it at tree level. So it can have some. Yeah, any level of correlation function. But you can have it some like loop level, as long as. I think the issue is not about the parity violation physics, but about inflation. So as long as you have these conditions. Yeah. So, any questions? So, okay. Do you have any question from this audience? So, if no, then maybe we can welcome the third speaker. Yeah. I need to. So we have the third talk, right? Okay, stop sharing.
哎，李笑言。
哎，在呢，在呢。Okay. Let me. Okay. Hello, everyone. So my name is Xiaoyan Li Xiaoyan, whatever. So yeah, I just joined the Tsinghua University in the automation department, and I graduated in two majors. One is environmental engineering, another is computational mathematics engineering. This name is pretty long, weird. Yeah, in Michigan State University. Just this year, this summer. Yes. So my research interest is AI for science. So basically, it's like use AI techniques to solve like scientific problems. So AI is very popular, and very powerful developed in recent years. But how to create or build a explainable AI is very, very challenging. And right now, so several, it's a very, very hot topic right now. And several very famous researchers are devoting in this area. So today I will just introduce what I did to use AI to solve the environmental problem in reality. So basically, it's a kind of application and how I designed to build the explainable AI. So in my video, and also I will also introduce some collaborations with the physics. So also some interesting topics. If anyone interested, we can work together. So that's that's kind of what I will introduce today. Okay, so the topic, kind of the research I did, in my PhD, it's like it's just the water quality monitoring and contaminants and analysis with carbon effect by machine learning. So here, I just introduction first, and the 3 projects I did in my PhD study and the future outlook. So water quality monitoring is it's very, very important research area in environmental engineering. So the reason is like here, it's water quality. You're referencing the drinking water, so tap water also or bottled water. So basically, it's just in Chinese is 饮用水，就我们喝的自来水或者是瓶装水这种and then the monitoring the quality is important because we want to know the water is okay or not, is at good quality or not good at quality. So also we all know there are many techniques, like people and agencies and like the governments and departments, they are monitoring the quality of the type of water every day. But why do I also try to devise new techniques? The reason is the old techniques are very expensive and time consuming. So how expensive they are? So basically, if you want to know the water quality of your for the type water, drinking water in your home, it will be $1,000 to $2,000 US dollars, for the full test, and it will take 2, 3, or 4 weeks for waiting for the result. So that's not very useful for the public, right? So we cannot wait for that long, especially sometimes we are concerned our water is good or not. The reason is maybe some issues, accident happened somewhere, and we don't know the water is good right now. So we want to know it right now. So we want an immediate answer, right? So that's the case. Also in some rural places or some in another developing country in Africa or something like that. So people want to roughly know. So here the method I'm developing is not very, very accurate, not accurate, not as accurate as the controversial, the conventional method, but here it's much cheaper and much faster. So here it's just showing what I the data I use. So basically here it's a SEM image. So we can think about so it's just a photograph or image. So here the pattern is just a droplet. Droplet, it's just a 3D, right? Okay, just droplet, and we can see the scale bar is 0.5 millimeter. So how it looks like, and all these small things here, so they are just the crystals. Crystals just contaminants, right? So there are different contaminants in this water sample. So when it dried, on the substrate is like a glass or something else. So we can see the pattern looks like here. So if the water is purely very, very clean, so we cannot see these crystals or something contaminants like this. But because they are not, so we can see these crystals. And the different crystals, they exhibit different pattern. So this one looks different from this one, right? And also something here, you can see small ones. So what I did in my research is using this pattern to infer what are the components of they are. So and what's the concentration of these contaminants they are. So that's the whole idea. And just briefly introduce the techniques used. So in my research, I used basically 2 techniques. One is coffee ring effect. This is a physics technique. I think many of you are very familiar with this technique. Another is machine learning. I will introduce later. So coffee ring effect, just in case someone not very very familiar or just fresh up. So it's just a example. We have a droplet of coffee. Originally, this is how this idea come up with. So we have a droplet of coffee, and this coffee drop on a substrate. Substrate is like a glass substrate or something similar to that, and it will dry, right? It will dry, and when it drying process, the contaminants, I mean the coffee particles or whatever in the droplets will stay there, right? And form a ring, several rings. This is the pattern. It's called the pattern, several rings. So this pattern is the signal. So it represents what they are in this droplet of the coffee, right? So here, the applications, basically there are 2 applications to use the coffee ring effect. One is suppressing and another is enhancing. So why? For example, they don't want coffee ring effect. Why? For example, so we when people talk about the chips, computer chips, so like the 卡脖子技术, right? Okay, the computer chips. So in producing the computer chips, we need the coating. The coating is several chemicals, placed on the chip, and we use the ultraviolet, to shine on it to make some, pattern or whatever. So if this chemical coating is not smooth, it's like it will, somewhere the particles will concentrate, cluster in somewhere, and there's no chemicals in another place. So that's a problem. So in that case, we want suppression of the coffee effect. And in other cases, for example, in this research I'm doing right now, I want to enhancing the coffee effect. Why? Because I want the contaminants concentrated in a specific location. For example, here or here. So then when the contaminant is concentrated, so I can get a stronger signal of these contaminants. So I will be able to know what they are and what concentration they are. So this is one example. Also, there are several other examples for enhancing, for example, the cancer detection. So especially in the early stage. So cancer is very hard to detect, right? So in the early stage, especially the proteins are very at proteins of the cancer at a very low concentration. It's called the signal of the biomarkers of the cancer, right? So because the concentration is very low, so we cannot detect the cancer at the very early stage. So it's bad for the human, right? So we want to know the cancer as soon as possible, as early as possible. So people try to concentrate them. So this is one method used in this area. Just briefly introduce how the machine learning used in water quality. So I'm doing, using machine learning to solve this water quality problem. So this is a roughly, slide showing that. So for example, SVM, supervisor machines, random forest, continuous neighbors, and FS, AN, CNN, all these methods, and also some other methods, RSTM and RDF and the generic algorithm, all these kind. I just, just let you show you what they are used. And I mean, if you are interested in some specific techniques, I don't think the area water quality is very related to here, but the techniques, they are very interesting. And another thing is like three areas for the machine learning used in water quality. One is the disinfection byproducts. So this is because we want to clean the water, in the final stage. So what I mean clean the water, after filtration, all this kind of absorption or whatever, we need to remove some bacteria. So we use like the UV light, to clean to kill the bacteria. But also we have chlorine, the disinfects. But when we adding these things, there will be some disinfection byproducts. This is 副产物. It's like they are bad for human health. So we want to know how much of these bad things produced. So this is some models doing that. Another is absorption. So in the water quality, water treatment process, there's absorption, 吸附作用, right? So people use this, different machine learning models to predict, for example, how effectively, the process did the absorption. So like how much is the conducting still remaining in the effluent, right? And what's the parameters should be, something like that. And the last one is filtration. So 过滤, this is the very, very basic, the idea for the water treatment. So basically, people use the model to predict after filtration, after filtration, what is still still remain in the effluent, something like that. So here, that's just the background. So here, the first project. The first project is pretty straightforward. So because this is the beginning of the deep learning and the machine learning arrival in these 10 years. So this one is just the first trial. So this is just to introduce how the covering effect works. So I have droplet and the water evaporates, and we can see different particles here, and the particles. Some particles already stay in the droplet. Some particles will some ions already originally dissolved in the water. So they are not really insoluble. They are soluble ions. So these ions will form crystals in the process of the water evaporation. And after the water evaporates, this newly formed the particles will deposit at different locations. So this is just showing you can see different the evaporation process. And in this process, because water evaporates, so there will form the microfluid of the water in this droplet. It's very, very small, it's microfluid, right? So then we can see this is a previous research. So different size of the particles will deposit at different locations. For example, you can see here, this one, and the blue one, green one, and the red one. So they are separated by the size of the particles. This is one research. So for the later research, not only just the particles deposited location, not only affected by the size, but also their properties. So charge, for example, and also the solvent, solvent properties, and also the substrate. This one, substrate properties. So it's a combination of all these kind of characteristics. So this is the example of my sample. So this is just the aluminum substrate. So this aluminum is just the aluba, right? Substrate, 基质, whatever. So I drop the droplet on this substrate and evaporate. I get this pattern. So this is how it looks like. And this is called residue of the evaporated water. And the surface of the aluminum slide is a mirror-like. So it's like a 镜子一样. It's a very, very shiny surface. It's really important. How I did experiment is very straightforward. I have aluminum substrate. I peel off the surface and I put the droplet on it and evaporate, and I get separated. You see, 1, 2, 3, 4. I get separated the particles deposited at different locations in this on this substrate surface. So this is so people will curious. So is this real? So how is the result, right? Is this convincible or not? So this is my real result. I'm showing what the real water, not synthetic, it's real water. So the water is collected in different locations. So this how they are treated, the different method, and from these locations and treated, and this is the pattern for I did the experiment. So by human eyes, right? So we can see they are different, right? This one is very different from this one, right? And MSU academic how it's very different from this Lansing set A, right? And from this one. So the next, I mean, by human eyes they are different. So is that possible to use the machine learning model to see, to classify them? So that's what I am trying to do in this first project. And of course, you are curious. You might curious. It's like they look different, but how about consistency? If the water from the same location, they look similar? Yeah, they look similar. I have the images to show later, but they look similar. And after collecting these images, I did some in my research, I did some, image, processing. So basically, remove some background and get some particles and did some calculations, the area and the numbers, parameters, all this kind of stuff. And here is one result showing. So this is a very, simple result. Just you can see different, sodium chlorine concentrations, different 3 concentrations, and areas are different, right? So this is basically, so this is a statistical analysis proving that they are different. So the question will be, is that possible to extract this difference or identify the difference by the machine learning model? Okay, so here what I did is like, firstly, I classified these water samples by the clustering method. This can mean clustering method. So here I clustered in 6 clusters, and so this is based on, this clustering is based on the concentrations of the contaminants, the different, the 污染物的浓度 based on that. So this is some data I measured, in the lab. So, and I draw this clustering result in 2 dimensions. It's by PCA, right? So here, and so you can see these ones. This is the first cluster, second cluster, for different numbers. So you might be curious, is this really, useful or whatever? Let's have a look. So for example, here we can see these samples clustered in the same, class. So they look a little bit similar, right? Not exactly the same, but you can see this is the kind of, the pattern here looks like, the tree, the white, the feather, something like that. And also this one looks similar here. And also this one. And let's go back, maybe go to here, this one. So these 3, you see, they look pretty similar. So there is some pattern consistency. So let's, I use this clustering result to do the classification by building a machine learning model. So yeah, this is the PCA just showing the same result, just in 3D dimension. So different clusters. So we can see some samples they cluster pretty very well in the same location. So some are not very good. Here, for example, the blue one, this one. So just showing how the machine learning model I used. This is CNN model. So here it's like I have the image and I have the convolution. I get the data from the image, and so this I use also max pooling activation and also the finally fully connected layer for the model. And this is the model I built. So it's the input is the image and output is 6 classes. So basically the model will tell me this image belongs to which class. So the class is just the clustering method I created earlier. And this is the result. So this is, so you can see we have the class 1 to class 6. This is prediction, right? By prediction is assigned by CNN model. So this is by the clustering. So this is the true, this is the true, the vertical one, and the horizontal one is the prediction. So if all the numbers in the diagonal, this one, so will be good, right? So it's everything is correct, but then there is some errors here. So for example, this one, and also like this one is 5 or 2 here. So look at the result. So this is the one of the 10 results here showing. I did 10 individual models. They are just all the same model, just initially differently. There is some randomness. So they are pretty, these 10 are very similar. So the highest one is this one, right? 82%, 82.5%, accuracy, and mostly here 77, something like that. So the accuracy is okay. I mean, it looks not that good, like 95, 99% accuracy, but this is a challenging problem. The one reason is my model is small. It's a very small model. So comparing to right now, the large language models popular right now, they are 大模型, it's like, I don't know, my model will be, their model is like, I don't know how to say, 1 million larger than my model, something like that, I guess. Yes. So after that is the second project. This project is not that interesting, so so I will just briefly introduce this one. So in my research, I collected the data and I built a model to know where is my sample from, right? What's the components of my sample? So the question is, how did I do the experiment? So what temperature, what the relative humidity, the condition I did the experiment. So this one is looking for the optimal condition, right? So of course, people are from different areas. They live in different conditions. But here, first, I want to find the optimal one. So so the question first is, what is the optimal condition? So optimal condition, I have 3 rules. I constructed 3 rules here. First is consistency. Consistency means like the water, they are from the same water sample, different water droplets, but the same water sample, they should be the same, right? Because they are the same water, just different droplets, right? Different trails. Secondly, is to separate different component particles maximally. So this means, so in my water sample, there are different contaminants. So I want to separate them as much as possible because they are different, right? If they are mixed together, the signals will interact. So because the signal interact, I don't know what they are. So it's a problem. So I want to separate them as much as possible. Also, I want to concentrate the crystals with the same components. And like last one, I want to separate different components. Then I want to concentrate the same component. So for example, if some particles, they are just sodium chloride, so I want this sodium chloride at the same location as much as possible. Because after they are at the same location, the signal is very strong. So I will know what's the components of they are. So that's basically the idea. And so I created this table for the 9 conditions, and I did the experiment under these 9 conditions. So this is the procedure. So doing experiment, I already have conditions. I need to have some water samples. So here I prepared 5 water samples, A, B, C, and D, E, and so I followed this paper diagram. So this is the drinking water, like how the occasions, anions, how the concentrations they are. So this is in environmental area. So basically, how people classify them, and this is showing my concentration of my samples. So I want to occupy as much as possible. So this is how it looks like. And to do this experiment, I need to control the temperature and relative humidity. So I built this this machine. So basically, this is automatic controlling the temperature and relative humidity. And also there is a auto sampler inside, because I cannot do the experiment by hand right now. If I use hand, I open this kind of thing and I use hand here. It's really not convenient. So showing one, let me see if we can play here. So this is how I did the experiment. So this is this is my sample here, and this is the syringe to extracting just the 2 micron liter, very small sample, and then move it to the desired location. So the location are calculated already. So this is a test. So then it will drop the droplet on the surface. The important thing is I don't want to drop the droplet too high from a very high location, because if it's very high, the droplet when it drops on the surface, on the aluminum surface, it will spread out everywhere, so it will fail. So I need to control the location, the distance from the tip, the syringe tip to the substrate surface very accurately. Okay. Okay. And after I did collecting the samples, I did the same procedure to get the particle information. And earlier I told you like how you might curious for same water sample. For example, this one, MSU academic building, for the same water sample, are they look different or the same? You can see they look similar, right? this one was, this is the 5 replicates. They are the same water sample, but the different droplets. Okay, so this is another sample. It's some water from Durand. Durand is a place, and Kalamazoo is another city. So you can see they are pretty similar for the rows, but different for the columns. So this is Peru, and this is just the the quality control. And so next is I did some the statistical analysis for my water samples. So this is the images. So this is now interesting. This is another statistical analysis, some result. So here I want to mention one thing. So in the analysis, this is the SEM or EDS, EDS measurement. So EDS basically it measures the locations, the signal of each element. For example, for the carbon here, so this is the water sample, and for the carbon, so here is like where is the in each location is there any carbon signals? And this is carbon is not sensitive, so the sulfur will be clear. This one. This is there are some stronger sulfur signals here, and this is chlorine, even stronger. So the important thing is like my water sample is like a ring, right? It's a ring. So the XYZ location Cartesian location is not suitable. So the polar coordinate is more suitable because this particle happened here. It's not different from particle happened here because it's the ring from the center of the droplet to the relative, the range, the distance to the particle. That's the important thing. So I did the transform of the coordinates. And this is also some statistical analysis. And like I said, I did this experiment under 9 conditions. So finally, the optimal condition is condition F here. So this one I selected. So the second project is done. I already got the optimal condition of my of this method. So the last question is like a more straight, is more useful or realistic. So in the first project, I did the research is like to build a model that can tell us what like class of this water sample. So basically where the water is from, right? So just make this clear. Let me introduce a little bit in Chinese. So 在第一个项目中，我建的这个模型吧，它告诉了我们这个水这个样本它是哪里来的，对吧？并且它因为来源不同，它这个就是组成就不同嘛。然后它经过不同的来源不同之后，它还经过不同的处理方式，因为各个水厂处理方式也不同，所以它就会分成不同的类。我那个模型就告诉它应该属于哪一类的，但是我们并不在乎它属于哪一类的，我们更在乎的是这些就是这个脏东西，对吧？这些污染物的浓度，是吧？浓度这个污染物是什么？浓度是什么？这是我们普通人所关心的问题。所以这个就是第3个项目，就是解决这个问题了。Okay, so back to English. So this is the project 3 I'm trying to do. So here is like I also created the tables from and prepared the water samples and build basically the same idea, build a model to predict the concentration. So how I build the model is here. So this is showing so this is big picture, right? Just showing how it looks like. So you can see different particles and the crystals, they look different in different locations. For example, this big one right here, and that some particles, some patterns here, and some small dots here, and some other patterns here. So this is small patterns. I mean, I'm not sure where I'm not very sure it's clear on your screen or something like that. So this is here is different from the substrate here, and also some dots in the center area. So because this water droplet, in the water drying process, the water is microfluid. They are moving, and the particles are forming. So it's a very, very complex process. So the particles, they have some particles formed earlier, some particles formed later, and some particles deposited on the ring, edge location. Some particles deposited in the middle location. So it's very complex, the process. And then I also collected the EDS. The EDS I introduced earlier. Also, it's just for different for elements. So the signals of the elements on this pattern. So this is how the EDS what they are. And so this is overlapping of the EDS and the SEM. SEM is the image. So I just use this image overlapping them manually. I manually overlapping them and to show what I mean. So for example, here this is EDS is for oxygen, right? 氧气, 氧, 对吧? So this is the oxygen has the signal here. We have we have the oxygen signal here, and also there's a particle here. So we know, oh, this particle contains oxygen. Okay, so here the same. Oh, this particle contains oxygen. But here, this particle doesn't contain oxygen. I mean, there's a little bit, but maybe that's the noise, right? So this is how the correlation between these two images. I mean, two data sets. So we can call it a multimedia, right? So it's a 多模态问题, right? So multimedia, and showing one result I collected here. So each row is a water sample. For example, this one, and this one. So we don't care about concentration here. I just want to show how they look like. So you can see we have oxygen here. This ring, the oxygen is maximally here, and sulfur. So sulfur, oxygen, sulfate, something like that. So also some sulfur has something inside, and magnesium, right, and chlorine. So there is some corresponding, between these elements. So this is important. Why? So for example, if we only use the first column, calcium, of course we can use calcium to predict the concentration of calcium, right? So because there is some noise, okay, if we remove the noise, we have some signal here in this ring, right? We can use this information to predict, estimate the concentration of the calcium. But is that the optimal? Is that perfect? No, because we all know there is some noise or something like that, and it cannot be perfect. And we can get some extra information from other elements because we have chlorine here. So calcium chloride is very possibly to form some calcium chloride particles, crystals, right? So this one can be helpful to predict calcium. The same idea, oxygen can be helpful to predict calcium, right? So this is the idea. I need this vision transformer, so to intervenely to transfer the information between each elements. So this is showing a larger image showing how the patterns look different. For example, this one and this one, small particles, and this one and this one. So what I did be creative analysis in this area. So area, I mean like coefficient effect. Coefficient effect is widely analyzed analysis in physics and chemistry. So also physical chemistry, yeah. So but no one has did this kind of analysis. They are more qualitatively. Quantitatively is much seldom, rare of this phenomenon. And maybe there are some like in the fluid there are some quantitative simulations. So here basically I separate this pattern. This is a droplet pattern. It looks big but pretty small, right? This is just a small droplet. So I separate them in 15 areas. So this is the first, second, third. So the third doesn't contain the second. Second doesn't contain the first. Okay, so it's individually. So this is the fifth. This is sixth. This is seventh. So why I did this? Because the crystals, they are deposited at different rings, right? So the particle deposited here is the same as the particle deposited here, right? So this particle will be different from the particle deposited here because they are in different rings. So of course, this is, you know, you might ask why 15, right? Why not 13? Why not 8? So 15 is so this is I tested several, several numbers for the classification. But 15 gives me the best result. Basically, so another reason use more and then less, because if I use more, I can combine them. For example, if 14 and 15 are the same, so I can combine these two rings, in later, analysis. But if originally they are in the same area, I cannot separate them anymore, right? So this is much better. So after that, I use the data from that, previous analysis method to create this result. So this is also the first, quantitative like analysis of the correlations of the elements. So what does that mean? So basically, you see, we have the 15 areas, right? And for each element, carbon, oxygen, sodium, they are separated by these 15, areas. For example, carbon. So from subring 1 to subring 15, so they are all carbon. This is carbon in the first area, carbon in the second area, carbon in the third area. So then I plot all of them together. So basically, I have 1, 2, 3, 4, 5, 6, 7 times 15, points, and I try to find the correlation between these 15 points. So we can see the strongest correlation is this one, subring 77 to this one, subring 32, right here, this one. So this is magnesium, right? So this is this one, what? Chlorine. So magnesium, chlorine, right? So this one, this is the second subring of this sodium. So this is the sodium, sodium chlorine. So this is second ring of the sodium, and this is the second ring of the chlorine. So it means the sodium chlorine is mostly happened in the second ring of the previous, the image. So that's basically the how to interpret this result. And after that, this is the model. Okay, let's look at something. Let's look at how I build the model. So I build several models. It's like make it more and more complex and more advanced. So how to do that? First is the input is the one SEM image. So basically, it's just RGB image. We can think about it's SEM, but we can think about it's RGB. It's like it gives us more information than cell phone because it's SEM, right? It's a scanning electron microscopy. So this is, but it's 3 channels. The very similar, the method to deal with to process them is exactly the same as RGB. And then I use the EDS module, and I estimation is to be 7 channels. Why 7 channels? Because from this one I estimated the concentrations of each element. I have 7 elements. So basically, I import 1 image. Here I get 7 images, from 1 image. So these 7 images. It's like they are the estimation of the elements, of the 7 elements I'm interested. Then I use the these 7 element locations. I calculate the concentration or the estimate concentration of these elements. So why does this make sense? So basically, it's like if think about that. If we have the locations of the elements, right? We have the locations, so we know how much they are, right? Because we already know where they are, so we know how many they are. How many they are is a simpler question than where they are, right? But you might ask, maybe they are stacked together, right? It's a 3D. So yes, that's possible. But if they are stacked together, the pattern will be different, right? So this model will learn this pattern, how they are stacked together. So this is the idea of this model. So this is the first one. So input 1 image, just training from end to end to get concentration of these elements. So this is the result. So for each element, so you can see the error bar, something like that. So let's look at second one. So first, the result looks better, right? Yeah. So this one result looks better because here, this is a two-stage estimation. So why it's a two-stage? First, the input is the same. The input is only still the same image. Okay, 3 channels. It's just like a cell phone image. And then in the middle, I check the estimation of the elements location first. So how to do that? I have the real EDS. Do you remember, like the black background and some colorful signals at once? So I have this real signal. So I use this real signal to train this model. So I want this one. Here the UEDS module could predict the locations of each element accurately. So in the previous one, I don't care they're accurate or not. But here I want it to be accurate. Then after this one, I calculate the concentrations. I estimate concentrations of each element. By doing this two-stage, method, the estimation is much accurate. So of course, I use the more information here, and this is for training, of course. But in the testing, I don't need this one because in the public, we don't have the EDS machine, like in our homes, right? This is pretty expensive. It's like I don't know how much, 1 million, 1 million, something like that. Yeah, it's very expensive. Yeah. And so this is the EDS. So like in the last slide, I said in the middle, I estimated the EDS. So here, this first row is the estimation of the EDS mapping for each element, right? For each element. And the second row is the target EDS mapping. And you can see this one. For example, this is oxygen. So this is the estimation of my method. And this is the real result of this, collected of the water sample. So yeah, they are not perfectly the same, but it captures the main point here, the main signals here. So this is a proof of this method. This is a proof that why this method works. This is another result showing the correlations between the elements. So this is the calcium and the carbon. So because in my water sample, I have the calcium and carbon is they are easier to find to form the crystals, right? And also oxygen and sulfur. So then I compare them. Okay, they are in the similar locations. You can see here, this is the empty area. There's no calcium and no carbon, right? So the correlation is pretty high. So this is showing, and this is the topology inner complex of this of the result. So basically, I have the signals for each element, and then so I connected the signals of the points of these elements. So looks like this will form the this gives me the idea of this crystals, where there are crystals will be in this area, crystal in this area, something like that. This is how to interpret the result. This is just some accuracy, false positive, false negative result for the each elements. So this is the third model I built. So it's also a two-stage model, but result is not good here. The difference from this one compared to the earlier second one, because earlier one I only output estimate concentration of each each element, right? For example, for the sodium, so the real concentration may be 10. So my prediction may be 9.5, something like that. But here, so in one model, I have 10 predicted concentration of each element. So basically, the concentration of sodium is 10, but I estimated 10 numbers, 0.9, 0.5, 0. And 10, 9.5, 9.6, 10 numbers. So I want to get an example of the result to reduce the error, standard deviation of the model. But this one requires I think the reason is this one requires more, training data. So that's why, because this model is much larger. So that's why the result is not good here. So before here, there is some sense in in the method, right? So there's a 2-stage, and the first stage explain something. So the next question is, can we do more? So here is I upgraded my model. So how to do that to make the model scientifically explainable of the deep learning model. So here, so these are the structures of each crystal. So crystals of each one, and these crystals are created in the Material Studio. So that's a software to create this kind of perfect crystal structures. And then I extracted this crystal structures by I get the relative the how to say it, elements locations and the angle of the the bond, all this kind of information from these structures. And then I used here the upper this area, you see the pre-trained crystal recognition module. I use this module to recognize here these unit cells. So unit cells, it's like some data, and I use this one to to recognize this unit cells. Basically, this module, they know what this crystals, which crystal they are. So okay, this is sodium chloride. Okay, this is calcium sulfate, something like that. So basically, here this module is capable to understand the crystal structure. So that's the idea of here. And then because this module is capable to distinguish these crystal structures, I use this knowledge in my 2-stage module, two-stage model here, and I use the output from this one, and to let this module to check which crystal it is, and then give the information back into my original model. This is the idea how I build the model. So the problem is I'm still training them, so it looks a little bit higher accuracy, but I'm still training them. There are several problems because this is looks 2-stage, but this one training is very hard because it's not in the end to end, from left to right. It's parallel, so the training is very delicate. So I need to tune the hyperparameters very carefully. But basically, this is the idea, and this is just the result showing the previous three methods, and this is another result. So basically, you can see the target is this one. So we want the result looks, the pattern looks similar to this one. So this is the first method, first model, not very good. The second model is much better. The third one is, the very useless, right? Yeah. And this is the model result of the comparison of these 3 methods. So here, of course, this the second method, this one, and 2 VIT and method. This is gives me the best result. And these are the evaluation metrics I used to evaluate the model performance. And this is the evaluation results. And lastly is the outer look. So this is when AI meets science. So lastly, I did the research is about water quality, and especially in the kind of like a machine, in the conservation, area. And also I did a research about, basically it's a competition. And fortunately, we get some good results in this competition also. So I mean, the overall, it's like the score is like we are the top 1 in this competition. So this is used the graph neural network. It's GNN model. So GNN model is like an input is a graph. It's like in the graph, it's like some points. These points can be anything, can be a human, can be a book, can be anything, and they are correlated. So like social media, like WeChat, some people they are friends, so because they are friends, there are some link between them. And then we have the output. So output is like anything. So we can output the age of the person. We can output like what kind of book they like to read, or the person, something like that. and this is the here, this is basically how the GNN works. And this is in the competition, we use the GNN model to do the task, the prediction. So basically, we have the input, it's like the, the DNA, the human DNA, it's a sequence, right? And then we use DNA to estimate what's the, like the gene expression, like, the signals of the, basically the signals of the RNA, like gene expression. So this is that's also a sequence. So, and this is how it works, like a true value, maybe this one, and the prediction is this one, and something like that. So it's also prediction and the question. And so here I'm doing a research with Dr. Song in Beida, and this is the quantum with the many body is estimation. I don't have a strong background in the quantum, this kind of area, but they give me the data and how to work quantum simulator for the state reconstruction, and also for me it's just many body, right? I just look at data. Okay, so what data you have? Okay, it's a graph data, and what result you want? You want like what class they are, or you want a number, or what you want, and do you have some labels already, or you don't? Maybe. So it's like I just look at these questions in the machine learning, perspective, and people look at the question in the maybe biology, physics, in environmental, or maybe chemistry, aspects. Another research project I'm doing is about a satellite, actually. So this is a new research. So we get some data. So if anyone they are interested and they have you have some good ideas, you can let me know. We can cooperate. So this is just to we just started this project recently. So basically we have the satellite optical adjustment data. So basically how the satellite, adjusted in the space. So the background is like we have many satellite, data. So they are, moving in this, in the space, right? So normally we don't need to care about them. We just, they just stay there. But in some special cases, for example, I don't know how to say that. Let me explain that in Chinese. Yeah, so 那个太阳磁暴的时候吧，我也说不上很准哈，就是说这个东西它会影响像地磁，然后地磁那个东西会影响它下面的那个大气的一些是那个磁压呀还是什么东西，它会影响这个卫星的运行，就是它会应该是用我的理解的话，它是将那个大气就是可能向上去就是往上顶了一下，然后大气向上顶了一下，它就会阻碍这个卫星的飞行，卫星就有更大的阻力，它阻力了有了之后，它就会向下降落，速下降，会降落。降落的话，他们这边就这公司会这边有那个数据，就要去调整这个卫星再回到原来的轨道上，就是我们有这样的数据。然后这样的数据呢，就我们是有这个卫星，我们有卫星怎么调整的这个数据，因为是要调整的嘛。所以呢，我们就想，能不能通过这个数据搞一个模型，对吧？去预测一下或者去估计一下，这样反推回到，就是从卫星的问题反推回到大气的问题，再返回到地磁的问题，再返回到最终的，不就是太阳这个磁暴的问题吗？是这样一个 idea 然后当然我们这边也是缺少一些，就是这个对于这个应该怎么说呢？应该算是地球科学吧，是不是这个领域啊，或者怎么样的这个天文这方面的一个背景、一个知识，所以呢，就也刚开始也是希望有那个感兴趣的人嘛，能加入我们，这样一个情况。然后the lastly is just some interesting findings. So road to AGI, right? So AGI is pretty popular in recent years. So we have the look at the past 300 years. So how the science developed. So the people developed the first microscope and they can see the insects. And now we have these big machines, right? So because this, they have the Nobel Prize, and also the AlphaFold, developed very very fast in recent years. So we want the artificial intelligence to be our new microscope. So earlier microscope is just a machine, right? It's like, we can touch it. It's a physical machine. But now the model can be a machine, right? So that's the idea. So the AlphaFold is already, this is one research. So they use AlphaFold to get some new, result of inspirations to design new drugs to solve, to kill the, to cure the disease. And this is another example of the AlphaFold. So basically, they use AlphaFold to found a new, the protein folding. The protein they are folded together, right? You can see different 3D structures. They found a new protein folding, method or protocol. So look at in the past 1 year, especially we have the agent of science for understanding. So right now we only use models to kind of the regression and to process the data. But the AI is like developed very fast. They can also to come up with some new mathematical ideas, and they can prove of this propositions. But of course there will be some limitations, but it's very interesting, and this will involve the question. So what is the science, right? So this is the history of the of the Chinese of our culture. What is the science? And next is from the scientific discovery to the scientific understanding, right? So science is developing, in recent 200 or 300 years. Many researchers did lots of research and on different areas, and people are maybe more and more understand what is science more and more deeper. So it's at the beginning, it's just we found something, but then more and more, deeper and deeper, we understand something. So that's the process of this scientific, process. And lastly, so it's maybe more physics. So it's like 光锥之内皆命运，光锥之外皆虚无。I don't need to explain this to all you guys. I think you all know and you all know this. So this is I need to explain this to some computer science students. Yeah. The highest activity of human being is content is learning for understanding, and because to understand is to be free. Yeah, this is my personal, contact information. If you are interested in the, you have questions, or you have some, you're interested in some projects I introduced, so we can, get in touch with me. Okay, that's all. Thank you. Wait.不好意思。
Yes, thank you for your talk.
Thank you.
Yes. So, if there are no questions,
yeah, I have a question. Could you hear me? Could you hear me?
Yeah.
Yes.
Yeah. I want to know, in your simulation, have you considered the effective interaction between different components?
Sorry, can I say again? Sorry.
Well.
喂，能听见？您说。
In the last pages, you mentioned the dynamics of many-body dynamics. So, in your simulation, have you already considered the interaction of different components?
Oh, you mean which one? You mean the physics one?
For example, the colloidal formation.
Colloidal
formation. Formation is a time influence process. So it's a typical dynamics. So in that process, have you already considered the effective interaction between different components?
Oh, you mean this one? Sorry.
Yeah, example. Yeah.
Oh,
yeah, yes.
Yeah. So so basically, it's in the many body,
dynamics.
scenario. Yeah. In the many body scenarios, it's like for example, maybe in this one, this is I just started. So this one is the competition we did. So we did consider the many body correlations between all of them because so this is you can see this one. It's a graph, right? So it's like many bodies, the points here. We call the nodes. So in the process, so in the calculation process, basically from here, from left to the right. So each point, so for example, can you see? Give me 1 second. So here for the red one, from here, red one. So the information of this red one is from itself, also the surroundings. This one, this one, this one, and this one. And this, the information from its surroundings, the neighbors, also from their neighbors. You know what I mean? So like from stage 1 to stage 2 to stage 3 or something like that.
Different stages.
Yes, the information is propagated, aggregated. So
So it's basically it's finite-wise force.
Finite-wise force.
It's the force between molecules.
Yes. Yes, you are right. Force between molecules and the distance and I use the bonds. In my research, previous research, I think you mean that one. And the bonds, the distance, and the angle, something like that, right?
Okay. So also in the process, have you considered some conservation? For example, particle number conservation.
Particle
number. Conservation.
Oh yes, I consider the particle number. Yes, that's right. Especially maybe here. So I explained. Maybe I didn't explain very clear. Let me see, where is it? I have. So for example, here, I have like these 7 elements, right? So I can predict the concentration of calcium, and maybe the model gave me the concentration is maybe 20 or maybe 100, 1 million, very large number. But the concentration cannot be 1 million, right? It's impossible. The maximum maybe just 100, right? So it's finite. So that's unreal, right? That's really unreal. And so if I incorporate the sulfur concentration, in information into this model, the sulfur, it will tell the model, no, it cannot be 1 million. The maximum is 20. So that's how to consider the conservation of the like the balance number of each. Yes, that's right.
Okay. Okay. Thank you very much.
Yeah, no problem. Yeah.
谢谢
谢谢。
行，那如果没有什么问题的话，那就在这个结束了吧。谢谢。